All right, so we are now ready to start talking about vectors and motion in 2 dimensions, right? So in this case, I will be using this PowerPoint that we have here. I normally don't do this, however, for this type of stuff, it's very important that we have nice, clear diagrams that you can see, and my artistic skills are not going to be up to the task for it. So we won't always do this, but for this type of stuff here, this is very nice that I can have these nice pictures to show you. So we are going to be talking about motion in 2 dimensions eventually. Before we do that, though, we need to kind of establish this idea of vectors in 2 dimensions, right? So now again, we have to think back to what our vectors are. What are the defining features of our vectors we're going to be dealing with? These objects, these essentially arrows, right, that you can draw on your paper. They have the two main features that they have are some sort of length and some sort of direction to them. And a good way to help visualize this kind of stuff in 2 dimensions, right? In 1 dimension, it's relatively simple. You either go backwards or forwards. In 2 dimensions, though, it gets a little bit trickier. So we'll start with this picture here to kind of help us visualize exactly what's going on, right? So we can have this top-down view of this map of some sort of city here, and we're going to say that now instead of just being able to walk either east or west or north and south, we're going to be able to go in all these different directions all at once, right? We can go left and right, we can go up and down, or again, you can think of it as east, west, north, south, however you want to view this. But in this case, we can now say that we're allowed to move around on this kind of 2 dimensional flat surface that we have here, right? So in this case, we're going to say someone starts out, they go 9 blocks east and they go 5 blocks north. And just a simple thing to start with is how we're going to figure out exactly how far they went and in what direction, right? So of course, it is okay to specify 9 blocks east, 5 blocks north. That will tell you everything else that you need to know. But we can also talk a little bit about what the total displacement is of someone walking around on this path, right? So when we're dealing with these vectors in 2 dimensions, as you can see from this picture here, right, we have our x-coordinate on the horizontal axis, we have our y-coordinate on the vertical axis, and as you can imagine, when we're dealing with this type of stuff, something that's going to be very helpful to us is our old friend Pythagoras, right? The Pythagorean theorem we're going to use a lot for this type of 2 dimensional stuff, right? With these vectors, we're going to be able to break them down into their x and y coordinates. And then, of course, if we want to know what the total length of that vector is, we can use this Pythagorean theorem that we have here that we should all be very familiar with, right? So if we have our x coordinate, we have our y coordinate. In this case, we have our sides a and b. We want to find c. We all know a squared plus b squared equals c squared. We can simply solve for c, and we can get the square root of a squared plus b squared, which in this case will give us something that looks like this, right? So we can say again, when we're talking about these 2 dimensional vectors, there's a couple different ways that we can talk about this, a couple different terms that we can use. That's going to be kind of some of the stuff that we're going to be dealing with here in this first section, right? So of course we can say that we went 9 blocks east and 5 blocks north, but this is also equivalent to saying that we went in a straight line, 10.3 blocks at an angle of 29.1 degrees above the horizontals. These are all kind of valid ways to get us to the same destination in this 2 dimensional picture, right? However you go about it, however you get there, either of these paths that you want to do, you can go north and then you can go east, you can go east and then you can go north, or you can just, again, imagine this picture here. We hop in a helicopter and fly over the city, right, in this direction of 10.3 blocks at a 29.1 degree angle. Either way, any of these paths will get us to the same displacement, right? So these are kind of all the things that we have to deal with, right? So the overall displacement vector, then again, we would say, with the vectors, we have to specify length and direction. The length of this vector, of our resultant vector in this case, would be 10.3 blocks, and the direction, of course, would be 29.1 degrees above the x-axis. It is important that we specify what this angle is in reference to, right? So we will want to pay attention to that kind of stuff. But yeah, so this kind of gets us into our first topic that we want to talk about is the conceptual addition of vectors, right? You can think of this picture here. You can have this one kind of resulting vector of the overall displacement of this person's path, this kind of 10.3 at a 29.1 degree angle, or you can think of it as we've added these two vectors, this 9 blocks east and this 5 block north vector here together, right? But when we're talking about this addition of vectors, we do want to specify a little bit about exactly what is going on. And that's the first thing that we have to learn how to do is kind of how we're going to be talking about these vectors and how we can add them and subtract them, since we're going to be doing all kinds of math with these vectors. And this is going to be relevant for our 2 dimensional motion, but these 2 dimensional vectors are going to come up over and over again for the rest of the semester. We're going to be doing this stuff a lot. So when we're talking about adding these vectors together, we can kind of think of it like this. We'll get into how we can do this mathematically in a little bit, but for now, let's just focus on the conceptual side of adding these vectors together, right? So basically, conceptually, what you're doing when you're adding these vectors together is you're using essentially the head to tail method, right? And you can do this graphically just to kind of help visualize what's going on, you can use a protractor, you can use a ruler, and if you do it this way, you will get accurate results for the additions of these vectors. We're not obviously going to do this. I'm not going to have you get your protractor and your ruler out. We have a better way to do it, but for now, this is just to kind of help us visualize exactly what is going on conceptually when we add these vectors together, right? So again, we can think of it as we have our first vector here, 9 units to the right in the positive x direction. Then we have our second vector that we're going to add, and which is 5 blocks in the positive y direction. And if we add those together, essentially what you're doing is you are drawing them tip to tail, right? So we have the head to tail method of graphically adding vectors is illustrated for the 2 displacements of the person walking in the city considered previously. So essentially all that means is, right, each vector you can just imagine it, you can visualize it as an arrow, right? And we're kind of adding these arrows together. And the way that we're going to do that is, again, each of these arrows has a direction that's pointing in and a length of the arrow, right? And if you want to add 2 of these arrows together, you just take the second one and stick it on to the end of the first one, right? So here's our first one. If I want to add this one to it, stick it onto the end there. And then the resulting vector that you get is wherever you end up at the very end of this drawing that you have, right? So we have vector 1 plus vector 2, and we can see here in this third picture, the overall resulting vector is, we start again where we started out, but wherever we end up, that's what our resulting vector is going to be. So again, this is known as the head to tail method. This is every time you add vectors together, every time you subtract vectors, we'll get into what that means. This is essentially what you're doing, right? When you're adding and subtracting these vectors together. Just from a conceptual standpoint. Of course, again, we're not going to use protractors and rulers for the rest of the semester, but for now, this is a good way to visualize exactly what is going on when we add these vectors together. So we can make this picture a little bit more complicated, sorry. And we can say, okay, we have 3 different vectors that we want to add together. We have vector A, 25 meters long at an angle of 49 degrees. We have vector B, which is 23 meters long at an angle of 15 degrees. Then we have vector C, which is 32 meters long at an angle of negative 68 degrees, or 68 degrees below the x-axis, however you want to specify that. And so if I want to add these together, right, you can just kind of think of it as how do you add together any other 3 numbers, right? You just kind of do one then the other, you just do the first 2 and then you add the third one to that, right? And with the vectors, it will work the exact same way, right? So conceptually, again, if you were to draw it out, you get your protractor out, you get your ruler out, you draw them very carefully. This is the picture that you would get, right? This tip to tail method, we have vector A plus vector B plus vector C, right? And so right now, again, we're just kind of just doing this stuff for displacements, right, to make it nice and easy. When we get into, we'll do some addition of other types of vectors as well, though, throughout the semester, and these same rules will all apply, rather, right? It's just the first thing to do is, again, just talk about different displacements as we walk along a path or something to kind of help visualize what is happening. So if you do that and you do that very carefully, and you get all your angles and your lengths correct, what you'll see is that you get a resultant vector that is about 50 meters long at an angle of 7 degrees below the x-axis, right? And so again, every time you add vectors together, this is really all you're doing. You just kind of draw them from one to the next and see where you end up. That is conceptually what is happening whenever we add these vectors. So yeah, so the good news about adding vectors together is the order that you add them in doesn't actually matter, right? So which is good for us. Again, it makes it nice and simple. Again, this works just like the addition of scalars that you're used to, right? And if you add 3 plus 5, it's the same as 5 plus 3. In this case, adding A plus B plus C is the same as adding C plus A plus B, right? Take a different path maybe, but the overall resultant vector that you get, the spot that you end up at as you draw these vectors tip to tail, is you do end up in the exact same spot, right? We still have this 50-meter long resultant vector at an angle of 7 degrees below the x-axis. So yeah, so that's kind of, again, how we add vectors together. We can also talk about subtracting vectors. As you may know, when you're subtracting, again, you can just think of it as adding the opposite of something. So when you're subtracting vectors, again, you can just kind of think of it as you need to figure out what the opposite of some vector is, right? So the negative vector is just another vector of the same magnitude but pointing in the opposite direction. So we have this picture here. Again, what we're saying is we have vector b, and then we have the vector negative b. They are the exact same length, but they are pointing in the exact opposite directions, right? So of course you can imagine then if I add b plus negative b, add them together, I get right back to where I was. I get a vector of length 0, right? So this is what you should get, right? B plus negative b should give you back to where you started, and this is what will happen, right? So again, same length, opposite direction. You can also think of it as 180 degrees in the other direction, right? Yeah, so if you just add 180 to the angle of whatever you started with for b, that will give you the direction of negative b, right? Same length, opposite direction for the negative of a vector. So similarly, we can then compute a minus b, basically the same way that we did a plus b, right? So again, as I said before, in this case, a minus b is just the same as adding a plus negative b. So if we have vector a, 27.5 meters at an angle of 66 degrees, we have vector b, which is 30 meters long at an angle of 112. The first thing you want to do, if you want to do a minus b, figure out what negative b is, right? So it'll look like this, right? We have 112 degrees here, so putting it in the opposite direction, that would be negative 68 degrees, or 68 degrees below the x-axis, however you want to think of it. Either way is fine. So now we've found negative b, now we can just add a plus negative b the same way that we have been doing before, right? Draw vector a, draw the vector negative b at the end of a, and we end up with something that looks like this. We have our resultant vector, 23 meters long, at an angle of 7.5 degrees below the x-axis. Of course, if you wanted to add a plus b, you could do that as well, and this is what that would look like, right? It's just the same as we had before. Now, instead we still draw a out first, and instead of doing negative b, we just do positive b, and we get this resulting vector here, just like we had before. All right, so that is how we're going to add and subtract vectors. That's what's going on conceptually. There is a couple different ways that we can also talk about these vectors, right? As I kind of have alluded to before, in that very first picture, right, we had our person walking along the city. We said that they go 9 blocks over and 5 blocks up. However, we can also say that they go 10.3 blocks at an angle of 29.1 degrees, right? So that's kind of 4 different things that we can talk about to describe one vector, right? Um, if you talk about the 9 and the 5, that's kind of talking about the x and the y coordinates of that vector. Whereas if you talk about the 10.3 and the 29.1, that would be talking about the length and direction of the vector, right? But all 4 things that we have, right? We have x component, y component, length and direction. We have 4 different ways to talk about this vector, but really they're all, you just need 2 of them, right? You're going to need 2 of them, and you can describe everything that you want to know about the vector. So how do you kind of go back and forth between talking about the vector in these different ways, right? So again, what we're going to have to do there is we need to use a lot of our trig. So in this case, this is kind of one way we can go back and forth, right? If we know the length of our vector and we know the angle of our vector, we can figure out the x component by saying this. We have the ax, right? This length in the x direction, right? The length in the x direction, right? So we have this overall length of our vector, but how far does it extend in the x direction is what we're concerned about in this case. We can say ax is equal to a, right, the total length of the vector times the cosine of this angle theta, right? And of course, we can do something similar for the y direction. We can say ay is equal to the total length times the sine of this angle here, right? So again, this is kind of how we define sine and cosine. Of course, you can do your SOHCAHTOA stuff. You can see, okay, this is the opposite, right? This is the adjacent, right? So on and so forth. However, it's important to remember sine of theta is defined as, you can do your algebra here. Sine of theta is defined as the ratio of this vertical side here, the length of this, divided by the total length of the vector, right? So that's kind of how you would solve for what sine of theta is. So in this case, when we're doing it, it does work out that we have, when we're using this angle, we have the x component you can get by doing a cosine of theta, the y component you can get by doing a sine of theta. This won't always necessarily be the case. Sometimes you'll have a different angle. So for instance, in this case, we're using this angle here in the bottom left of our triangle. If we use this angle up here at the top of our triangle, though, you'd actually have to flip these, right? Then you would say ax equals a times the sine of this angle up here, and you say ay equals a times the cosine of this angle up here. So the thing to remember is cosine always goes with the adjacent, the side of the triangle adjacent to the angle, right? You can measure 2 different angles. So if I want adjacent to this angle theta, then it would be cosine gives me the x direction. If I want the opposite side of this angle theta, then I would say ay equals a sine of theta. I'm only specifying this, again, it might be a little bit confusing. I just don't want you to get caught up in this idea that the x component is you always get by using cosine, and the y component you always get by using sine. In this case, that is true. In a lot of cases, that will be true. But again, we'll see some examples at some point in a later video where you do have a different angle that you're trying to specify. And so it is important to remember cosine goes with the side adjacent, right? In this case, the adjacent side does happen to be x, and sine goes with the side opposite to the angle, right? So just to make sure we understand what is going on with that. Um, so yeah, so again, we can kind of go back to that very first picture that I showed you. We can kind of apply it to here. Certainly we can see the x component is a cosine of theta. So if you do 10.3 times the cosine of 29.1, sure enough, you do get 9 blocks to the east, right? So again, this vector here, this resultant vector that we have, this 10.3 to angle 29.1 degrees, it extends in both the x direction and the y direction. So we can see we can use our trig if we have this 10.3 and this 29.1, we can use our trig to see just exactly how far it extends in each direction. Right? You can do the same thing for the y component. A y equals a sine of theta, 10.3 times sine of 29.1, and sure enough, you do get your 5 blocks north. So again, this is how you would, if you start with this 10.3 and this 29.1, this is how you can figure out what the x and the y components are. Depending on what kind of problem you're doing, again, I'll show you a bunch of examples where sometimes you want certain information or whatever. But for now, just if you have a vector, if you have a vector in 2 dimensions, you have the length, you have the direction, and you want the x and y component, this method here is how you're going to do it, right? Keep track of your trig functions, use your sine and cosine accordingly. However, if you already have the x and y and you want the length and the direction, we can do that too, right? We need to be able to go back and forth between these kind of two different ways that we have to talk about our vector, right? So we can say, okay, if I have the x direction, if I have the y direction, let's say I have this 9 blocks and I have this 5 blocks. Okay, it's not the same picture in this case. It'd be more like 5 and 9, but that's okay. But if I have the x component and I have the y component, again, I can figure out the length of this, as we all know from before. Use the Pythagorean theorem, right? This is kind of like your a squared. This is your b squared. This length is like your c squared that you have in that formula. You can solve for this length a by saying the square root of your x component squared plus your y component squared. Of course, then if you want this angle here, again, you have to keep track of which one is the opposite, which one's the adjacent. But you can say, remember again, you have SOHCAHTOA, tangent is the opposite over adjacent. So the tangent of theta is tangent of this theta is the opposite side, which in this case is y, divided by the adjacent side, which is ax. Take the inverse tangent of both sides, right? The inverse tangent just kind of undoes the tangent. So you have theta then equals the inverse tangent of ay over ax, right? So again, with these two methods that you have, it's really important to make sure that we can go back and forth, right? We have 4 different ways, 4 different pieces of information that we can use to describe this vector. We have the length, we have the direction, we have the x component, and we have the y component. However, again, it is important to remember that as long as you have 2 of them, you can figure out what the other 2 are, right? It's just 2 different kind of ways to talk about these this one vector, right? And it actually does work. You don't have to have the x and y or the length and direction. You can actually go as long as you have any 2 pieces of information, you can actually figure out the other one. So that's something to think about. And again, we'll see examples where this will come up. But a good exercise to think about now would be, okay, if I have the angle here, what happens if I have theta and the x component, right? How can I get back to the y component and the length? And it is possible to do, again, you just have to do your trig. We can go back here. If I have this angle theta and I have the x component, one simple way you could do it would be just use this formula here, right? You can just kind of rearrange it. Before we were saying, okay, if we have our length and direction, this is how we solve for ax, but I can also rearrange this and I can solve for a, right? Let's say I have ax and I have this angle, right? So if for some reason I have this horizontal length and then I have this angle here, if those are the 2 pieces of information I have, I can still figure out how to get to this length a, right? You would simply do ax divided by cosine of theta, right? Just do your simple algebra, solve for this length a here. And you can say a is equal to then the x component ax divided by the cosine of theta, and that will give you the length of the vector. Similarly, you can do something the same for y, and you can play around with it. Any combination you want. You have this 4 pieces of information again, length, direction, x and y component. Any 2 of those, it doesn't matter which 2 you have, any 2 different combinations of those, you can figure out what the other 2 are. All right, so now that we know a little bit about how to go back and forth between these different types of ways to talk about our vectors, we have the length, direction, x and y component. We're now finally ready to start adding these vectors together in a much more consistent way than actually having to worry about our ruler and our protractor, right? Again, if you wanted to do it, if you wanted to add a plus b in this case here, and you wanted to get r, the resultant vector between these two, it would be totally valid to be very precise, draw it out on paper, make sure you get your lengths and your angles correct, and you would get um, uh, the correct vector. However, we want to make sure we can do it a little bit more consistently than that. We want to do it in a much more analytical method. So in this case, if we have A and B, and we want to figure out how to get R, the way that we can do this mathematically is by this. What we can recognize is that um, when I have a plus b, if we break these vectors down into their components, we can add the components together to get the new components of our new vector. So what do I mean by that? If I have vector A and I have vector B, right, what I really have is, and these are two-dimensional vectors, what I really have, this formula here, this A plus B equals R, this is really actually two formulas that we have hidden in this one formula, right? What we're saying is the x component of A plus the x component of B is equal to the x component of r. So you could write one that says ax plus bx equals rx. And you can also say, similarly, the y component of a plus the y component of b is equal to the y component of r, right? So there's really two formulas. You have one for the x direction and one for the y direction, and it does work out just as simply as you would want it. Ax plus bx equals rx, ay plus by equals ry, right? So it's really kind of, it's two different formulas kind of baked into this one two-dimensional vector formula that we have here, right? So again, just visually you can see it. So we have a plus b, ax and bx together are going to give us how far r extends in the x direction, right? It has to, just kind of based on how we have this drawn and how we define these vectors. Ay again plus by also has to be how far this vector extends in the y direction. So when you have a and b, you're trying to find r, the first thing to do if you want to add them together, you want to do it in a much more consistent method than actually bothering with your ruler and your protractor. Figure out what ax is, figure out what bx is, add those together, and that will give you rx, right? Figure out what ay is, figure out what by is, and that will give you ry, right? That'll give you the y component of r, and of course then the x component of r as well. So again, we have these two formulas here. We have Rx is going to be equal to Ax plus Bx. We have Ry is going to be equal to Ay plus By. So depending on what you have, sometimes this will be a very complicated step. There might be a lot of trig that you have to do. But sometimes you'll already have the vectors in their components and it'll be nice and simple, right? So again, it is a lot of trig that we have to worry about, but we can do each step. We just have to break it down and take it slowly, right? So you have the length of our vector A is 53. The angle of our vector A is 20 degrees. The length of B is 34. The angle of B is 63. And so with that information, we can then figure out what the x component of A is. We can figure out what the x component of B is. And we can simply add those together. Do the same for the y components, and you will get both the x and y component of your vector r, right? So again, it looks like this. This is a very good frame to stop on for a little bit and make sure we take in all this information that we have, right? So again, AX is 49.2, BX is 15.4. If I add 49.2 plus 15.4, I get 65.2 meters. This is, again, the x component of your vector r, your resultant vector r of a plus b, right? Do the same thing for the y component. You have 18.1 plus 30.3, and you get 48.4 meters in the y direction, right? So of course, what this would give us, then we can do our trig. Right now I have the x and y components of r. I can do my trig, I can do my Pythagorean theorem, I can take my inverse tangent, and I can figure out that the magnitude of r, you can double check this for yourself, the magnitude of r is going to be 81.2 meters, and its direction is going to be 36.6 degrees north of east, right? Or in this case, above the x-axis, depending on how you want to think about it, right? So yeah, so again, this is how you would add these vectors together in this much more analytical method. Don't bother with the ruler or the protractor. Just simply do the trig every time. When you go to subtract them, it'll work the exact same way, right? If you want to have a minus b in this case, we can see it'll work the same as our tip to tail method. You would just simply take the x component of a minus the x component of b, and that would give you your new resultant vector, your new resultant x component. And you can do ay minus by, and that'll give you the new component in the y direction, right? So it might be a lot of work, it might be kind of tedious, but from a conceptual standpoint, again, this addition of vectors, this addition and subtraction of vectors, it does follow very similarly to this regular scalar addition that you're used to, right? But now you're just doing, you're essentially you're doing this regular addition and subtraction, you're just doing it in two different directions at once, right? So that's kind of the thing you have to keep track of. When I have this two-dimensional vector equation here, a minus b equals r, this is really kind of two one-dimensional equations baked into each other, right? We have ay minus by equals ry, and we have ax minus bx equals rx, right? So this is going to be how we're going to add and subtract these vectors together. The next thing we'll then talk about is some of the physical situations, right? We've been doing a lot of math. We haven't really done a whole lot of physics in this section just yet. We're going to be talking about different situations in physics where we would use this two-dimensional addition and subtraction of vectors.